Hello everyone, my name is Simon, and today I'm going to introduce you to myoglobin. Myoglobin is a protein which exists in your muscles, and its primary job is to store oxygen. How it does this is it has a little iron molecule in its center, and it takes oxygen molecules and it places them on that iron molecule. Now, in order to bind with oxygen, that iron molecule needs to be protected from the water that's outside of the myoglobin. And so what myoglobin does is it has a bunch of structural elements that allows it to accomplish this task. That is, it creates a little waterproof pocket inside itself to safely store that iron molecule. Now, scientists were curious how this worked and how myoglobin accomplishes this. And this presented them with a bit of a challenge. You see, if they tried to look at that myoglobin using the light that you and I use to see, they wouldn't be able to get a good picture of it. The light that we work with is much too long of a wavelength to observe this myoglobin. It would just go right around it and you wouldn't be able to get any useful information. So instead, they turned it to something called synchrotron radiation. Synchrotron radiation is radiation that is produced when you accelerate a charged particle that is traveling at extremely high velocities. The frequency of this radiation is directly related to the velocity at which the particle is traveling, which means that if you put a particle in a particle accelerator and spin it up extremely quickly, then you're able to produce extremely high-frequency light. The particle accelerator that I was doing my research at was CHESS at Cornell. CHESS at Cornell is actually a little unique in that it accelerates positrons, which are the opposite charge equivalent to electrons, instead of, electrons. But it works in exactly the same way as a typical synchrotron. Even with these fancy synchrotrons, though, we can't just shine the light directly at them to observe myoglobin. Instead, we need to go through a process called crystallography. Crystallography is the process of using diffraction on crystals of your substance. So what we do is we place myoglobin into a crystal. A crystal is simply just an ordered, repeated structure made up of a singular molecule. Now, what we do is we send that light into this crystal. Now, light has this funny property where, since it is a wave, it is an electromagnetic wave to be specific, it has constructive and destructive interference. That is, if you have two light waves that are in phase with each other, that is, the peaks line up with the peaks and the troughs line up with the troughs, then they will produce a larger wave. And you have two light waves that are out of phase with each other, that is, a peak lines up with a trough and vice versa, then they will cancel each other out. So what we can do is after shining this light through the crystal, we get a bunch of interference patterns. We can then use a mathematical process called a Fourier transform to figure out an electron density map for our myoglobin protein. This allows us to figure out our structure and determine what myoglobin looks like. I'd like to thank the NSF and the CLASSE REU at Cornell for supporting my research. This has been my presentation on myoglobin and X-ray crystallography, and I hope you have as much fun learning about it as I have. Goodbye.